Good morning. Today we are going to have an asynchronous counter, design of an asynchronous counter, and this is a 3-bit ripple counter. 3-bit ripple counter in the sense it is counting like this 000, 001, 010, 011, 10, just like our counting numbers from 0 to 7 and then to 0. That means there is a 3-bit ripple counter. Say when you have a 0 to 1, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0 to 1, 1 to 0, 0. That means here this is state number, this is flip flop number 0. Suppose that this is flip flop number 0. This is flip flop 1. This is not 1, flip flop 0. This is f of 1 and this is f of 2, flop 2. That means output of flip flop 2 is q2. That means q2 is the output of this flip flop, q1 is the output of this flip flop, and q0 is the output of this flip flop. See, this q0 is frequently changing. That means from 0 to 1, 1 to 0, 0 to 1, 1 to 0. That means after each clock pulse, this is changing. After each clock pulse, this is changing means here we are using a negative edge triggered T flip flop. That means here this is negative edge, this is another negative edge, this is another negative edge, this is another negative edge, and this is another negative edge. And when there is a change from, that means initially that will be in state q0, and when you have, that means here this is the clock, this is the clock input, and for this clock input, if this clock is from level 1 to level 0, that means this is the negative edge, this is the negative edge, and this is a negative edge triggered flip flop, and then the state of this is changing as this is t is equal to 1. T is equal to 1 means whatever is the earlier output, it has to switch to a new or complementing, it is complementing that. When t is equal to 1, the previous state has to be complemented. When t is equal to 0, it is storing the previous value, and if it is t is equal to 1, then it will complement the previous value. Here, initially, the state was q0, and up to this point, it is q0. And when this t is equal to 1, what will happen? It will switch to a new state, and that is staying in the same state. And the next negative edge is here, and in that state it is again switching states, and it is now switching to state q0, and it is staying in the same state, and the next negative edge is here, and it is switching to this state, and when the next negative edge comes, it is switching to state q0. Now it is staying in the same state. Now the next negative edge, it is switching to this state and it is staying in the same state. Suppose that the next negative edge is here, then it is switching to state q0 and something like that. That means initially this is 0, this is 1, this is 0, 1, 0, 1, and something like that, and like that. Now, this Q0 is given as the input to, or that is given as the clock input of the first flip flop. That means the output Q0 is given as the input or clock input of the first flip flop. In that case, this Q0 is acting as the clock of this. That means that is again when t is equal to 1. The t input is fixed as 1. That means if there is a positive edge, if there is a negative edge trigger, then whatever is stored as q1, that has to be flipped. or that is to be complemented. Suppose that initially this will be Q1. Suppose that in that Q1 is 0, then when this Q0 switches from 1 to 0, see here we have a negative edge for this Q0, this is a negative edge, and this is another negative edge, and this is another negative edge. Okay. So when this one switches from 1 to 0, what will happen? This Q1, initially this will be in state Q1, and when this Q0 switches from 1 to 0, that's a negative edge, and using this we have the clock input of the first flip flop is this, and at the same time this is switching to state Q1, not state 1, and the next edge is here, next negative edge is here, until then it is staying in the same state, and when there is a trigger negative edge, then it switches to this state, staying in the same state. Here it is switching to new state, staying in the same state, something like that. So here this is 0, this is 1, this is 0, and this is 1. Okay. Now here for this Q1, this is the negative edge. For this Q1, this is the negative edge. And see here, Q1 is given as the clock input of flip flop 2. As this is a negative edge triggered flip flop, as this is a negative edge triggered flip flop, whenever there is a state change from 1 to 0 for this Q1, then this Q2 will be changed. That means whenever Q1 changes from 1 to 0, this Q2 is complemented. Here in this figure, we have only one transition from 1 to 0 for this Q1, and initially suppose that we have state Q0, and up to this point it is staying in this state, and it is switching to new state, and it is staying in the same state. Okay. See, this is 0, this is 1, and as I told you, this is Q2, Q1, Q0. So here, see, what is this? 0, 0, 0. That means this is 0. What is this? Here, this is state 0. This is state 0 because Q2 is 0, Q1 is 0, and Q0 is 0. Now, here see, Q2 is 0, Q1 is 0, and Q0 is 1. That means 0, 0, 1. This is 1. This is 1. And what about this? Here, this is 0, this is 1, 0. That means here this is 0, 0, 0. This is 0, 0, 1. This is 0, 1, 0, which is given as 2. What about here? 0, 1, 1. 0, 1, 1 is 0, 1, 1, which is 3. What about here? It is 1, 0, 0, which is 1, 0, 0, which is 4. And here it is 1, 0, 1. That is 1, 0, 1. That is 4, 5. And you can continue like this. You can continue like this. And this is the table. You can complete this timing diagram. This is called the timing diagram of 3-bit ripple counter, and this is the pictorial representation, or this is the circuit, and this is the timing diagram of 3-bit ripple counter, and you can easily design that. And in this case, this is the state diagram. That means can have this much number of states, 7, 8 different states, and 0, 0, 0 to 1, 0, 0, 1, etc. etc. And for this, we can have an asynchronous counter, 3-bit ripple counter. This is an up counter. Up counter means from 0, 0, 0 to 0, 0, 1, 0, 1, 0, etc. something like that. And here, see, here this is frequently changing 0 to 1 to 0 to 1 to 0, etc. Here, from there is a 1 to 0 change. Here 1 to 0 change is there. Then this is complemented. When Q0 is changing from 1 to 0, there is a change for Q1. That means, see, here there is no change from it is if as there is a change from 1 to 0, this bit is changing. Another 1 to 0 changes 1 to 0. Here this bit has changed. Here we have 1 to 0 change. Here it is changing from 0 to 1. Here also we have 1 to 0 change. Then this bit has changed from 1 to 0. Now, see here, if there is a 1 to 0 change, that means here you have a 1 to 0 change. At that point in time, you have to complement Q2. Now, here also we have 1 to 0 change, then we have to complement this value. And this is and that is all about a 3-bit ripple counter. It's an asynchronous counter, and here we have implemented this using negative edge triggered T flip flop, and this is the timing diagram for that. Can complete important point is here a binary counter can be used to divide the input frequency by some power of 2. For example, suppose that here the frequency of this clock is say f. Then that say here the frequency of this Q0 will be, if clock is having frequency f, Q0 is having frequency f by 2. This is having frequency f by 2, and this is having Q1 is having frequency f by 4, and Q2 is having frequency f by 8. This is f by 2 raised to 0, this is f by 2 raised to 1, this is f by 2 square, and this is f by 2 cube. Okay, that means this counter can be used to divide your frequency by a power of 2. That means if you want to, suppose that you have a ripple counter, and suppose that an input a clock is given, and if you want to divide that frequency into 2, 4, 8, 16, etc., you can make use of this. You can make use of this circuit. That means here suppose that the frequency of this clock is f, then the frequency of this will be f by 2, the frequency of this Q1 will be f by 4, and frequency of Q2 will be f by 8. And this is the pattern, and that is why this is called, this 3-bit ripple counter is otherwise called modulo 2 raised to n counter, modulo 2 raised to n counter, or divide by 2 raised to n counter. These are the two synonyms for 3-bit ripple counter. Okay.